The title of the paper is Towards a Rigorous Statistical Analysis of Empirical Password Datasets. Our speaker for this paper is Peiyuan Liu, who's a PhD student at Purdue. Let's give a round of applause to Peiyuan.
So, hi everyone, I'm Peiyuan Liu. I'm a PhD student at Purdue University. Today I'll present our paper Towards the Rigorous Statistical Analysis of Empirical Password Datasets. This is a joint work with my advisor, Jeremiah Blocki. Over the past decade, data breaches have exposed billions of user passwords to the dangerous threat of offline brute force attacks. Here we list an incomplete list of password breaches at major companies. To mitigate these attacks, many defense techniques have been applied, such as stronger password hashing algorithms and more complex restrictions that force users to pick stronger passwords. How expensive does a password hashing algorithm need to be to deter this offline attacker? Does imposing restrictions help strengthen the password distribution? To answer these questions, a common way is to consider an attacker who wants to guess a random user's password. Following Kirchhoff's principle, we assume the attacker knows the password distribution. Then the best strategy of this attacker is to always check the next most probable guess. The key challenge of characterizing this attacker's guessing curve is, as defenders, we don't know the distribution. Formally, we define this attacker's guessing curve lambda g as the probability that an attacker can crack a random user's password within g guesses. Here is an example of what lambda g looks like if we give the top 3 most probable passwords in a distribution. So then the research question we focus on is how to characterize this lambda g without knowing the distribution. Well, as defenders, although we don't know the distribution, we do have a lot of publicly available password samples from the distribution. Using these samples, there have been several attempts to estimate lambda g. One common heuristic to estimate lambda g is to use the empirical distribution derived from a bridge password dataset, which we call lambda hat g. Here is an example of lambda hat g, where we use the password frequency in the sample set to estimate the password probability. A downside to this approach is that it is likely to overestimate the guessing curve lambda g. Indeed, we have lambda hat g always equals to 1 whenever the guessing number g is greater than n, even when the password distribution is very strong that contains much more than n passwords. So another natural attempt is to fix a password cracking model and assume that the attacker uses this model to generate password guesses. Such state-of-the-art models include but not limited to probabilistic context-free grammars, Markov models, neural networks, and softwares like John the Ripper and Hashcat. However, the attacker's model may be more sophisticated than any publicly available model. Also, the attacker may improve the model over time, so this approach may underestimate lambda g. To avoid these problems and obtain theoretical guarantee for the guessing curve lambda g, in this paper, we developed 4 statistically rigorous techniques to upper and lower bound the guessing curve, which are proved to be true with very high confidence. The first technique we propose is called frequency upper bound. Using concentration bounds, we can prove that the guessing curve lambda g is upper bounded by the empirical distribution lambda hat g plus the small term epsilon. The second technique is called sampling lower bound. Given a password sample set S, we randomly partition the set into 2 parts D1 and D2. Here we consider an attacker using D1 as a dictionary to crack passwords in D2. We can prove that the proportion of passwords that are cracked in D2 within G guesses minus small term is the lower bounded of the guessing curve with high probability. Notice that the lower bound will plateau after we try all guesses all guesses in D1. To continue to crack more passwords in D2, we need to expand the dictionary, which leads to our third technique called extended lower bound. The extended lower bound is similar to sampling lower bound, except that we use a password cracking model to be an actual dictionary to crack passwords in D2 after we're trying all guesses in D1. This allows us to extend our provable lower bound on lambda G for any large guessing number G. The last technique we propose is the linear programming approach. The objective of our LP is to find a distribution that maximizes or minimizes lambda G, subject to the constraint that the distribution is sufficiently consistent with our sample set S. The key linear constraint of our LP is derived from good Turing estimation. We prove with high confidence that this expected probability mass of all unseen passwords that do not appear in the sample set can be upper and lower bounded by the proportion of unique passwords in the sample set, along with the small term epsilon. The final linear programming algorithm we propose in our paper is more sophisticated than what I presented, and if you're interested, please see our paper for more details. Now, let me show you what these bounds look like on a plot. In the empirical analysis, we plot all our bounds using 8 empirical password datasets to evaluate the performance. Here is an example of our bounds generated using 000 web host dataset. We guarantee that each bound holds with at least 99% of confidence. We can observe that this frequency upper bound and sampling lower bound are very tight when the guessing number G is not very large. Then, as the two bounds diverge, the linear programming approach provides the tighter bounds. Then for extremely large guessing number G, the extended lower bound provides a useful lower bound. We find that there is one prior work that also times the lower bound lambda G, and we can show that our bounds outperform the prior lower bound. Also, we notice that there is still a gap between our upper and lower bound when the guessing number is very large. And this is due to the large probability mass of unseen passwords in the sample set. We think this gap can be reduced by either increasing the number of samples or developing better password cracking models. Now let's compare our bounds with the two approaches of estimating guessing curve, lambda G, which are the empirical distribution and password cracking models. Our bounds can prove that empirical distribution closely approximates the guessing curve lambda G of an attacker who knows the distribution, as long as the guessing number is not too large. By contrast, for a large value of guessing number, we can demonstrate with high confidence that the empirical distribution significantly overestimates the guessing curve. In this case, the empirical distribution should not be used to estimate lambda G. We also find that our lower bounds are often higher than the guessing curves generated using the state-of-the-art password cracking models. This indicates that there is still room to improve the password cracking models to be more guess efficient. In the analysis, we also compared our bounds with this CDF law estimate, which are used to estimate lambda G using this expression. Our bounds shows that, in this example, Zipf's law curve is provably inaccurate at most of the points. Only within this small region where Zipf's law is between our upper and lower bounds, this estimate is proved to be accurate, likely accurate. In the end, I'd like to demonstrate some potential applications of our techniques. One application would be tuning hash cost parameters. Suppose that an organization is considering doubling the cost of a password hashing function. With these constant resources, the attacker can only try half of the guesses after doubling the cost. However, this will require the organization to invest additional computing resources to handle user authentications. Therefore, the organization will only consider making this change if the security gain lambda g minus lambda g over 2 is substantial enough. Our techniques can be used to upper and lower bound this security gain as shown here. In general, we can upper and lower bound the security gain of increasing hash cost by any times, such as 16 times or 32 times, as shown in this figure. Another application would be identifying secure password composition policies which yield password distributions that are more resistant to password cracking attacks. Yahoo Password Frequency Corpus allows us to compare password distributions of user passwords that are selected before and after applying this 6-character minimum policy. Using our bounds, we show in the plot that applying this 6-character minimum policy can slightly increase the resistance to offline attacks. We also evaluate several other password policies in our paper and demonstrate more plots. And due to time limit, if you're interested, please see our paper for more contents. Yeah, that's all for this talk. Thanks for listening, and I'm happy to take any questions.
Questions? All right, let me ask the first question. So on your slide 15, you mentioned that lambda g is much more easier to estimate if g, which is the number of guesses, is small. Based on maybe your empirical results, what is a good value of g for which you can estimate lambda g accurately?
You mean what's a good value of g of?
Yeah, what would be some good values of g? Ideally, in most web services, the number of guesses allowed would be maybe 2 or 3, after which you have a lockout, right?
Yeah, so I think there are 2 attacks. One is online attack, one is offline attack. For online attacks, we would like to evaluate the guessing number g to be small because usually the website will lock out after we try several guesses. But for offline attacks, where the attacker will obtain a large amount of password guesses and have a lot of time to crack those hashes, then we will need to look into large guessing numbers based on the attacker's computing resources.
Okay.
Yeah.
So I didn't quite understand why would you say this is a rigorous analysis. So can you clarify this?
You mean why this is a rigorous analysis?
Yeah. In one of the slides, you claimed that this analysis is rigorous, right?
Yes, because all those bounds we proved that all our bounds to analyze this guessing curve lambda g can hold with very high confidence, like 99% of confidence. And these are always rigorous math proofs. So that's why we said this is rigorous analysis.
Okay, right. Thank you.
Okay, thanks.
Other questions? All right, if not, let's give a round of applause to Peiyuan. Thank you.